In 2019, humanity photographed a black hole for the first time in history. It was M87, a supermassive black hole 6.5 billion times the mass of our Sun, sitting at the center of a galaxy 55 million light-years away. The image was blurry, orange, and incomplete, but it confirmed that the most extreme object in the observable universe actually existed and looked roughly like the physics said it should. James Webb Space Telescope just looked at it again, and what the infrared images showed, published in September 2025 after James Webb pointed its most sensitive cameras at M87 in June 2024, was something that the models didn't predict and that nobody has a complete explanation for. A second jet, moving in the opposite direction. Faint, fast, and until now, completely invisible. A counterjet retreating from us at near light speed, carrying material away from the black hole in a direction we had never seen before. Detectable only because Webb's infrared cameras can see through the overwhelming glare of 55 million light-years of starlight in ways that no previous telescope could manage. The universe's most famous black hole has been hiding something directly behind it, and the more closely Webb looks, the stranger the picture becomes. M87 is not like most black holes. Most supermassive black holes sit quietly at the centers of their galaxies, consuming material slowly and producing relatively modest amounts of radiation. M87 is different in almost every way that matters. At 6.5 billion solar masses, it is one of the most massive black holes we have confirmed anywhere in the observable universe. For context, the black hole at the center of our own Milky Way, Sagittarius A star, is approximately 4 million solar masses. M87's black hole is over 1,000 times more massive than the one at the center of our own galaxy. But mass alone doesn't explain why M87 has been one of the most studied objects in the universe for over a century. The reason astronomers keep pointing telescopes at it is the jet. From the core of M87, a stream of charged particles extends outward for several thousand light-years, moving at velocities that approach the speed of light. The jet was first detected in 1918, more than a century ago, when astronomer Heber Curtis noticed a curious straight ray extending from the galaxy's core in photographic plates. He had no idea what he was looking at. Over the following 100 years, astronomers gradually understood that what Curtis had photographed was material being accelerated to near light speed by the magnetic fields around an active supermassive black hole and launched into intergalactic space. The jet is not a metaphor or a simplification. It is a physical structure, a luminous column of plasma extending thousands of light-years into space, so energetic that it affects the gas and star formation across the entire galaxy and beyond. And until Webb looked at it in infrared last year, we had only ever seen one side of it. When a black hole launches a jet, conservation of momentum and the physics of the magnetic field acceleration process require that it launch material in both directions simultaneously. One jet moves toward us, one counterjet moves away. The jet moving toward us is bright because of a phenomenon called relativistic beaming. When something moves toward you at near light speed, its emitted light gets compressed and amplified, appearing far brighter than it would from a stationary source. The counterjet moving away from us experiences the opposite effect. Its light is dimmed and stretched, becoming so faint that it effectively disappears against the background. For decades, astronomers knew the counterjet should exist. They could not detect it in visible light or radio wavelengths at the resolution needed to separate it from the galaxy's overwhelming background glow. Webb's near-infrared camera changed that. By imaging M87 at 4 wavelengths of infrared light, and then using computational models to subtract the galaxy's stellar light, essentially removing the haze of 55 million years of starlight to isolate just the jet structure, the team could see, for the first time in infrared, the counterjet extending approximately 6,000 light-years from the black hole in the opposite direction. And the jet itself revealed structures that had been invisible before. Helical lanes, spiral patterns winding through the jet material. Distinct bright knots where particles are accelerating to particularly high energies. A feature called HST1, located close to the black hole's core, resolved into two separate substructures with different physical properties, suggesting that the acceleration process is more complex and spatially varied than previous models assumed. The jet is not a smooth column of plasma. It is structured. It has internal geometry. And now that Webb has shown us what that geometry looks like in infrared, the question of how a black hole produces and sustains a jet of this complexity at this scale over this distance has become significantly harder to answer. What that means for understanding black holes. The first image of M87 in 2019 confirmed the black hole's existence. Webb's infrared imaging in 2025 confirmed that what the black hole is doing with the material it processes is far more organized and far more violent than the existing models fully account for. Separate from the James Webb jet observations, a paper published earlier in 2025 established something that transforms the physical picture of M87's black hole entirely. M87's black hole is spinning at approximately 80% of the maximum possible rotation rate for any black hole. The theoretical maximum rotation is called the Kerr limit, the speed at which a black hole's event horizon would be rotating at the speed of light itself, which is the physical ceiling. At 80% of that limit, M87's black hole is not just massive. It is a rapidly rotating engine, carrying angular momentum on a scale that is difficult to translate into human terms. Rotation changes everything about how a black hole interacts with surrounding space. A spinning black hole drags space-time itself around with it in a phenomenon called frame dragging, the lens-Thirring effect, warping the geometry of space in its immediate environment in ways that a non-rotating black hole does not. This frame dragging is believed to be the primary mechanism that collimates the jet, that keeps the plasma column focused and directed over thousands of light years rather than dispersing outward in all directions. The connection between the spin rate and the jet structure is direct. A faster spinning black hole extracts more rotational energy from the surrounding space-time and converts it into jet power. At 80% of the Kerr limit, M87's black hole is transferring an enormous amount of its rotational energy into the jet continuously, over timescales that exceed the age of our solar system. The helical structures Webb detected in the jet are now interpretable as a signature of this frame dragging, the magnetic field lines twisting around the rotation axis as they are dragged by the rotating spacetime, imprinting their helical geometry on the plasma that flows along them. The jet is not just coming from the black hole, it is encoding the black hole's rotation in its structure. Every spiral in the helical lanes Webb photographed is a record of how fast M87's black hole is spinning. Here's what the James Webb observations have not resolved, because this is where the science actually is. The jet acceleration mechanism, the specific process by which particles are taken from near rest and accelerated to 99% of the speed of light, remains incompletely understood. The leading model involves the magnetic field structure around the black hole's ergosphere, the region of rotating spacetime just outside the event horizon, extracting rotational energy through a process called the Blandford-Znaiec mechanism. The model is well developed theoretically. Observational confirmation at the level of detail that would constitute proof has not been achieved. The internal structure Webb revealed in HST1, the region near the black hole's core where the jet is most energetic, has two distinct substructures with different spectral properties that don't fit cleanly into the current acceleration models. Something is happening in the jet close to the black hole that the models don't fully predict. And the counterjet, now detected for the first time in infrared, is moving away from us at near light speed, which means we will never get the same quality of data from it that we have from the main jet. It is faint, stretched, and difficult to resolve even for Webb. What it would show us about the symmetric structure of the launch mechanism, if we could see it as clearly as the approaching jet, remains one of the open questions that future telescopes will be designed to address. M87's black hole has been observed for over a century. It was the first black hole ever directly photographed. It has now been imaged by the most powerful infrared telescope ever built. And the more precisely we observe it, the more precisely we can articulate what we don't yet understand. The first photograph of a black hole in 2019 showed us a blurry ring of light around a dark shadow. It confirmed a prediction. It won a Nobel Prize, and it answered the question of whether supermassive black holes look like the theory said they should. James Webb's 2024 observations answered a different kind of question. Not whether the black hole exists and looks right, but what it is actually doing and how complex that process is at the level of detail that only infrared imaging can reveal. A counterjet invisible for a century, now photographed for the first time. Helical internal structures encoding the rotation of a black hole spinning at 80% of the physical maximum. Acceleration mechanisms that approach but do not fully reach the predictions of our best models. A jet that has been active for longer than Earth has existed, extending thousands of light years into intergalactic space, structured in ways that the blurry orange image from 2019 could not have suggested. The universe's most famous black hole has been sitting 55 million light years away, doing all of this for as long as our solar system has existed. We have been pointing telescopes at it for over a century, and in 2025, we are still finding things in the data that we did not expect to see. That is the honest state of our understanding of black holes. Not a solved problem, not a settled science. A phenomenon that reveals new structure every time we build a better instrument and look more carefully at something we thought we already understood. The most dangerous object in the universe, and we're only just beginning to understand it.